Now for optimization algorithms determine if we are going to have a negative probability or a positive probability based on the input of the data in respect to the weights and biases. This is a separate calculation from the activation function. And then right here, optimization algorithms play a significant role in shaping the behavior. So they shape the behavior of neurons within a network, ultimately just grouping them together between negative and positive probabilities. They guide the learning process by adjusting weights which indirectly affect the probabilities associated with neuron activities to determine if a positive or negative probability is occurring. And these probabilities can be thought of as the likelihood of a neuron producing a positive or negative output. So we are just grouping probabilities together. Through the iterative process of training, optimization algorithms group neurons together based on their behavior, influencing whether they tend to produce positive or negative probabilities, and this grouping is essential for the network to learn and make accurate predictions. Overall, with respect to the weights and biases from the parameters set by the model, we're able to understand the network's overall performance. So, and also for further context as well, optimization algorithms are widely used, especially in a method called backpropagation, which we will cover in a future video focusing on the training of neural networks. But right now we're just focusing on the overall structure behind the process of a neural network prior to going further depth in the training. But again, for future reference, we will have that video. And common optimization algorithms used for the process would be gradient descent, stochastic gradient descent, mini-batch gradient descent, ADAM, which stands for adaptive moment estimation, RMS prop, which means the root mean square propagation, ADAGRAD, which means adaptive gradient, ADA-delta, adaptive gradient delta, and improvement over ADAGRAD, and NADAM, which stands for Nesterov accelerated adaptive moment estimation. And we have the following acronym over here. Now, to be able to go over and understand further in depth between gradient descent is a first-order iterative optimization algorithm used to find the local minimum of a differentiable function. The idea is to take small proportional steps in the direction of the negative gradient, the steepest descent, of the objective function with respect to the model parameters. So we are looking for the steepest descent of the objective function and this is technically called gradient descent because it uses the information of the gradient, the steepness of our given slope, to decide the direction, and descent because it aims to descend to the lowest point. So it is descending to the lowest point. As well. And the learning rate defines the size of these steps, and choosing the right learning rate is crucial, as too small of a rate can lead to slow convergence. Also, we have to be crucial about the learning rate to avoid slow convergence. And if we have too large of a gradient descent, that means we would overshoot. output. There we go. And to be able to break down how the formula is actually built and constructed, so theta refers to the parameter vector of the model, which needs to be optimized. And the following symbol refers to the learning rate, which controls the size of the steps taken towards a minimum loss function. So controls the size of steps taken forward to minimize, or to the minimum of the loss function. And this following group over here, J theta, refers to the gradient of the loss function, referred to as J, with respect to the parameter vector. Respect to the parameter vector. One second. And now let's over to stochastic gradient descent. So stochastic gradient descent is a variation of gradient descent, except for it runs faster by updating the model's parameters using only a single sample. So stochastic calculus is, stochastic gradient descent is like gradient descent. It processes faster though. Alright, by updating the model's parameters to use a single set. Slash subset of the full data set. This allows for much faster iterations, but the trade-off is that the updates are noisier, which can lead to resultant fluctuations and potentially only converging to a neighbor of the minimum rather than the minimum itself. Stochastic gradient descent works well when the data set is large and redundant, so works well with large and redundant data, as the noisy steps can help to escape local minima and possibly leading to better generalization of unseen data. better generalization of unseen data. And to go over the symbols, so stochastic gradient, the theta, is the parameter vector. Eta, this symbol, eta, is the learning rate. And then this bad boy here x for I, and then y, I plus b, which is the gradient of the loss function with respect to theta. With respect to theta. Stochastic gradient descent is evaluated at a single set of the full data set. There we go. And now let's head over to mini batch gradient descent. And so mini batch gradient descent is an algorithm in the middle ground between batch gradient descent and stochastic gradient descent. So it is between batch gradient descent and stochastic, stochastic gradient descent. In mini-batch gradient descent, the update of the parameter is performed on a small random subset of the full dataset. So utilizes a small random subset of the full dataset. Utilizes a small random subset of the full dataset and updates parameters. This combines the advantages of both stochastic gradient descent and batch gradient descent by reducing the variance of the parameter updates. So reduces variance on parameter updates. Leading to more stable convergence, and by being more computationally efficient than using the full data set, lead to stable convergence. Then using the full data set. The size of the mini batch is a hyperparameter that can affect the performance of the conversion speed. So the size of the hyperparameter affects speed. Affects conversion speed. And to go over and break down the following symbols that we have. So mini batch gradient descent, the following symbols are. So we have theta, which we all know it's going to be the parameter vector. Eta is the learning rate. And then this bad boy over here. I wonder if I could just copy and paste the whole thing. I think I can. Let's do that. Just write it out. There we go. That's better. That looks prettier. This one is a gradient of the loss function. With respect to theta, as well, evaluated a small subset batch. And for evaluated at small subset batch. And now let's move over to the ADAM or adaptive moment. Now to go over the adaptive moment estimation or ADAM optimization algorithm. ADAM is an adaptive learning rate optimization algorithm designed specifically for training deep neural networks. It combines the advantages of two other extensions of stochastic gradient descent. First, so combines two components of stochastic gradient descent First, similar to the root mean square propagation optimization algorithm, it maintains a per parameter learning rate that improves performance on problems with sparse gradients. So like natural language and computer vision problems. So maintains a per parameter learning rate which improves performance on problems with sparse gradients. So it's thorough. Second, similar to stochastic gradient descent with momentum, it also keeps track of the decaying average of past gradients. So it keeps track of decaying averages for past gradients. However, Adam also computes the decaying average of past square gradients. So, but calculates the decay average of past squared gradients, which is used to scale the learning rate for each parameter. And this means that parameters with large gradients will have their efficient and effective learning rate be reduced, while parameters with small gradients will have their effective learning rate increased. So increases / decreases learning rates for small and large, respectively, gradients. So we focus on speed and accuracy of prediction while minimizing the loss function. Focus on speed and thoroughness for training. Adam overall usually requires little to no manual tuning of the learning rate and often works well with default settings. No manual tuning needed. And now to go over the formula. Adam is comprised of M MT view T M T T. We have beta 1, it looks like. U. And then epsilon as well. So M of t represents the first moment. Estimate. V of t represents the second moment estimate. M cap t represents the bias corrected first moment estimate. Bias corrected with first via t and bias corrected second. Beta 1, exponential decay rates for moment estimates. Rates for moment estimates. And then we have our learning rate. Learning rate, and epsilon represents a small constant to prevent division by 0. And now let's head over to root mean square propagation. And feel free to take a screenshot of each of the components of our optimization algorithms. And now going over root mean square propagation. Root mean square propagation is an adaptive learning rate method designed to resolve the radically diminishing learning rates commonly in autograd. So it's an adaptive learning rate improvement from autograd. And it does so by modifying the general gradient descent by dividing the learning rate for a weight by a running average of the magnitudes of recent gradients for that weight. So modifies the general gradient descent and by dividing the learning rate for a weight by a running average. So learning weight. For a weight. By a running average of the magnitudes of recent rates. So recent running average, or running average of recent. Gradients. For the same weight. This means that the algorithm divides the learning rate by an exponentially decaying average of the squared gradients, hence the square root. And this operation prevents the learning rate from decreasing too fast. Prevents learning rate from decreasing too fast. And is beneficial for problems with very noisy / sparse gradients. So very useful for noisy / sparse gradients. And root mean square propagation can work well in scenarios where autograd falters due to aggressive and monotonically decreasing learning rates. So we got a good speed of learning rates. For higher accuracy. And to go over the symbols for root mean square propagation, Following symbols we have will be, we have e of g squared with the absolute value with respect to time. Which the running average of the square gradients. And then we have mu. We have the following symbol, as we know, which is the learning rate. Then we have epsilon, a small constant for numerical stability. Constant for numerical stability. And G of t which equals the gradient of the loss function with respect to the input vector at a given step in time. So gradient of loss function with respect to the input vector represented by theta at time step t. What is... Alright, there we go. Now let me just clean this up. There we go. And let's move over to our next part, autograd. Now to go over adaptive gradient descent, or the adaptive gradient algorithm, autograd is an algorithm for gradient-based optimization that adapts the learning rate to the parameters. So, gradient-based and adapts the learning rate to the parameters, performing larger updates for infrequent and smaller updates for frequent parameters. Perform larger updates for infrequency for infrequent parameters and perform smaller updates with frequent parameters. It is particularly suited for dealing with sparse data, so great for sparse data. The benefit of autograd is that it eliminates the need to manually tune the learning rate, as we discussed before. However, its accumulation of the squared gradients in the denominator can lead to excessively rapid decrease in the effective learning rate. And it can prematurely converge to suboptimal solutions, which is why it may not be well suited for training deep neural networks, but it is good to be able to know whenever we have sparse data that we can use the adaptive gradient descent if we need a quick means of classification. So it's faster for optimizing classification, trade-off with speed and accuracy. And to go over the following symbols to help break down, it will be the following. Let me just move this up. All right, the following symbols will be for autograd, so G of T I is equal to the sum of squares of gradients with respect to theta up to time step t, and then mu refers to, as we know, the learning rate. Epsilon is a constant. Constant to prevent division by zero. Similar to the root mean square propagation. And finally G of T, lowercase. So we have this symbol right here, G of T. With respect to the input, it's going to be the gradient of the loss function with respect to input vector and at time step t. Let me just clean this up for you folks. And now let's move over to our next part, ADA delta. So ADA delta, or adaptive gradient delta, is an extension of autograd that seeks to reduce its aggressive, monotonically decreasing learning rate. So, extension of autograd, but decreases monotonous nature of speed with autograd. Instead of summing up all past square gradients, auto delta restricts the window of accumulated past gradients to a fixed size. So establishes a fixed size using only the most recent gradients. Unlike summing all past squares. This makes it robust to the main weakness of autograd. The auto delta update rule is similar to the root mean square propagation, but with a more sophisticated way of changing the learning rates. It eliminates the need to set a default learning rate, which is a significant advantage over autograd and root mean square. So it changes the learning rate. For more adaptive data that isn't as monotonous and no default learning rate, keeping the speed but considering noise. And let's go over the symbols. So the following symbols that we have for auto delta will be the following: E of G squared as a value with respect to time versus running average of square gradients. The following symbol here is P, refers to the decay rate similar to beta. In atom optimizer. Then we have delta theta t, which is a parameter update vector at a specific time. Vector at time step t. And then epsilon, on the other hand, a constant for numerical stability. Constant for numerical stability. And now let's head over to our next part. Feel free to take a screenshot. But now we will be adapting to our next optimizing algorithm, Nesterov accelerated adaptive moment estimation, or NADAM. So NADAM, or Nesterov Accelerated Adaptive Moment Estimation, combines the benefits of Nesterov Accelerated Gradient, so combines Nesterov Accelerated Gradient and Atom Optimizer. So we have Atom and Nesterov Accelerated Gradient. I'll also have a link for that. By incorporating Nesterov momentum into Atom. So they combine Nesterov momentum into Atom, and taking into account the look ahead property of Nesterov. So they combine momentum and look ahead. Property. This helps to not only gain the benefits of the adaptive learning rates from Atom, but also the accelerated gradient from Nesterov. So strong, beneficial learning gradient. From Nesterov. And adaptive learning rates from Atom. So we speed and thoroughness. And overall, it makes it more efficient than any other of the following solo methods alone. NADAM has been shown to outperform Atom, actually, in some cases, especially in problems with very noisy gradient or with problems with fine-tuning of the solution. So, works very well with noisy gradient or problems requiring fine tuning of solution. And so let's go over the symbols. There we go. So for the following symbols, NADAM has M of T, M cap T, G cap T, beta 1, nu, phi cap T, and epsilon. So let me just move this over a little bit more to be able to help. There we go. There we go. Okay. So M of T is running average of the gradients. M, M cap t is the corrected running average of the gradients. G cap t is gradient of Nesterov momentum. Beta 1 is the decay rate of momentum. Term. U is, as we know, the learning rate. V cap t is the running average of the square gradients, so running average of squared gradients. Epsilon, a small constant to avoid division by 0. Let me just clean this up now. There we go. Feel free to take a screenshot. And now we will move over to our concept examples. And so yeah, thank you very much for taking time to watch this. If you found this video helpful, be sure and feel free to please like and subscribe. And if you have any other questions, feel free to put it in the comment section. And as always, take care. Cheers. Bye-bye.